In this video, I'm going to be going over your guys' notes for Unit 5, or at least the beginning of them, and kind of walking you guys through the simulation that you guys are going to be looking at as you because you guys are not able to be in class to do the in-lab. I want you to be able to still get the same experience as the other students. The lab is not something that you guys are going to be graded on, but it will kind of help you to give you some experience with these concepts, as well as it will help you to fill out your notes. So I'm going to briefly go through the first couple sections of your notes, and then I'm going to show you guys interactive and where you guys can kind of make your claims. First of all, just a little bit of a review from what we talked about in Unit 4 in the last semester. What happens to a car on a track if the forces are balanced? So there are two possible situations here. So either we can have the forces being balanced, and that's because the object is stopped, or we can have the forces be balanced and the object be moving at a constant speed. So for the situation number 1, where the object is stopped, our net force is still 0. So my force diagram would just be the force normal going up, force gravity going down, right? So if I have a calculator sitting in my hand, the force normal pushing up on it, pushing it up, is the same as the force gravity pushing it down, right? And this object is stopped. I could also have it be going at a constant speed, and that would have the exact same force diagram, right? I would have force normal going up, force gravity going down, and there's no force pushing it to the left or to the right, right? There's no force friction pulling it back. There's no force pushing it forward. It's just kind of moving on its own at a constant speed. So that's situation number 2. The forces are balanced, and the object is moving at a constant speed. Our net force here is still 0. We don't have one force that wins. So we have 0 net force here. We just have one force pushing up, one force pushing down. You could also have said for either of them, that we have a force pushing forward and then an equal force friction going in the opposite direction, and those two forces canceling out. That would have been fine for either of these two force diagrams as well. Really, any force diagram where the forces are all equal but in opposite directions would count for these. The object is moving at a constant speed or stopped. If the forces are balanced. If the forces are unbalanced, this is where we are really going to focus in this unit. If the forces are unbalanced, that means the object will accelerate in whichever way the forces aren't balanced, right? Whichever way has our net force is where the object will accelerate. So in this case, I now have my calculator and I'm applying a force push on it. So we have force normal going up, force gravity going down, and then I have a force push or force pull to the right, and that is where the object will accelerate. It will accelerate to the right. So I have a picture here of what could be an example of an unbalanced force. So in this case, the cart on the track is being pulled to the right by this rope, and this rope looks like it's attached to a pulley, and then this rope is being pulled down by this block here. Right, so you let go of the block at the very end, and then the cart will move down the track. Now, this is what is called an Atwood's machine. So I have an interactive here for you guys. I did put the link above the notes so you can check that out. But really what this is, again, the weight dangling off, in this case, the blue weight, and then there's the red cart on the track, and there's that pulley. So as soon as I let the weight go, you'll notice that the cart accelerates. Right, and what you should be able to notice is that this acceleration with a small weight looks different than the acceleration with the big weight. Right, so I'll have you guys be looking at this interactive in a second, but I gotta finish our notes. Anyway, so this is our setup. This is what is called an Atwood's machine. So we have the pulley here, and we have a cart being pulled down a track, and notice that it's accelerating. So if you look up here at the dots, this is kind of like a motion map. If you look at the dots are getting further and further apart for both those two objects. So I'm going to get back to our notes. So for number 3, it says draw the force diagram of the cart and the force diagram of the weight, right? The dangling weight or the box here. And this is where I think it's very important for you guys to remember. At any point, you can pause this video or rewatch the video if, as you're filling this out on your own on Cami, if that does not make sense. If you don't know how to use Cami, this is also a good point to point out. I do have materials on my Canvas page that will help you guys to figure out how to work Cami and how to submit things. So please check that out above. And when you guys are done, I do want you guys spending some time looking through my Canvas page and making sure that you completely understand everything. But anyway, the two force diagrams. So my force diagram on the left is the cart. So I have the force normal pushing it up, force gravity pushing it down. That's not really interesting. They kind of balance out. Then on the cart, we're going to say this is a frictionless surface, so we're ignoring friction. If there was friction, there'd be a little bit pushing left, but we're ignoring friction. So it's just force tension, right? That rope pulling it to the right. And you'll see why I have the 2 tick marks in a second. But first, the block. So the block is being pulled up by tension, and then the force gravity is pulling it down. Notice force gravity is greater than this force tension because it's accelerating down, right? The reason that I have the 2 tick marks on my 2 force tensions here is to show that those 2 force tensions are equal, right? Because if we look at any force tension, the force tension in any rope is going to be equal throughout the entire rope. So the rope is pulling tight here on the cart, but it's also pulling tight in the same amount on the block, okay? So what force causes the cart to accelerate? So we're just focused on the cart right now. We're ignoring the block over here. The only force that causes the cart to accelerate is the force tension, because the force normal and the force gravity, the only other 2 forces acting on it, are canceling each other out in up and down directions. So force tension is what causes the cart to accelerate. If we look at the whole system, though, so we look at both objects, those 2 force tensions cancel out, and then we have our force normal and force gravity kind of cancel out or balance each other. So the only force that isn't really balanced or countered by something is this force gravity on the block. Okay, so the force gravity on the block is what is not being balanced in any way, so that must be the force that causes the entire system to accelerate. So the reason that I'm pointing that out is if we want to change how much force is being applied to this cart, we would need to change this force gravity, because that's what's causing the acceleration. Okay, so when you're doing the simulation, if you want to see the effect of force on acceleration, you need to change the amount of weight on this block. Okay, that's what the people in class are going to be doing. So on the false quiz, you guys were asked about the relationship between mass, force, and acceleration. So the 2 main things that people in class are looking at is how mass affects the acceleration of an object and how the force applied to an object affects the acceleration of an object. So those are the 2 things that we're going to be looking at in the lab. So what I want you guys doing in the simulation to create your own claims in this final 2 slots is you guys are going to be changing or looking at mass versus acceleration and seeing how that's affected, right? Is it when you have more mass? So I'm going to actually flip back here. Is it when you have more mass on the cart? All right, I'm going to change that. When you have more mass on the cart, is that going to make it go faster or slower? Right, so if I have more mass, notice I'm changing mass here. Notice I'm not changing it so it doesn't have wheels. I'm just changing mass. So if you change mass, does that have an impact on the speed? So you only have to run this like 1 time. Okay. And then I'm going to restart it. So like look at the amount of time it took. Drag it all the way back. Look at the amount of time it took when it was more massive. So that's the first thing that you guys are going to be doing, and you are going to fill out your claim here. Right? The more mass you have, the less acceleration, or the more mass you have, the more acceleration, right? Or the more mass you have, it doesn't really affect the acceleration. So that's the first thing you guys are doing, filling out that claim based off the simulation. And then the second thing, if I add more mass to the weight on the end, so in this case, you're changing the force right? Because we talked about how that's the force causing the acceleration, how that force affects acceleration. Is it the more force, the more acceleration, or whatever? So in this case, you're keeping the mass of the system the same. So you're keeping, doesn't matter what you choose. You could choose to have no weight there. And then all you're doing is saying, okay, this is my least amount of force I can put on it. Start, drag it back, and then increase this, boom, increase it again. All right, so that's pretty much what you guys are doing. And again, you're creating a claim here about how force impacts acceleration. And this is what we will talk about when you guys are first in class on Wednesday or Thursday or day 2. But for the rest of the time, I want you guys spending some time exploring my Canvas, making sure that you completely understand how to use all the materials in Canvas, how to turn things in my class. This is really your time to kind of explore, make sure that you really understand what's happening. Please let me know if you guys have any questions on this, and have a good day.